Today we're diving into one of the coolest puzzles in artificial intelligence. How do you train a machine learning model on data that it is literally not allowed to see?
It really does sound like a bit of a magic trick, doesn't it? I mean, think about it. Can an AI model learn from millions, and I mean millions, of patient records spread all over the world without ever actually laying eyes on that incredibly sensitive private information? It sounds impossible. But the solution is already here, and it's changing everything.
So here's the heart of the issue. Hospitals everywhere are sitting on an absolute goldmine of data. We're talking health records, lab results, images, you name it. This stuff could unlock massive breakthroughs in how we diagnose diseases. But, for very good reason, all of that data is locked down tight by privacy laws in what we call data silos. They can't share it. So this amazing treasure of collective human knowledge just sits there completely untapped.
So how do you solve a paradox like that? Well, it required flipping the entire problem on its head. Instead of trying to bring all the data to one place, what if you could send the AI model to the data?
And this is an idea called federated learning. The concept is actually beautifully simple, but it is revolutionary. Instead of collecting all the data in one central pot, you just don't. You leave it where it is, safe and sound. The AI model is the thing that travels. It kind of goes on a world tour, learning a little bit from each stop along the way. Okay, so here's the play-by-play. It starts with a central server that sends out a sort of student AI model. Each hospital takes that model and trains it only on their own private data. Now, here's the key part. They don't send any of that sensitive data back. They only send back the learnings, basically the mathematical updates to the model. The central server then collects all these little updates, combines them to create a much smarter global model, and then sends that improved version back out for another round. And the cycle just keeps repeating.
And listen, this isn't some futuristic theory. You are probably using it every single day. You know when your phone's keyboard just gets better and better at predicting what you're about to type? Yep, that's federated learning. It's also helping self-driving cars learn from the experiences of the entire fleet, and it's even predicting when machines in a factory might break down, all without having to pool all that sensitive data together.
But while federated learning was a huge leap forward, it wasn't quite the perfect solution. As researchers started to really poke and prod at it, they found some hidden risks that could actually undermine the whole point of keeping everything private in the first place. So here were the main issues. First off, you've still got that one central server running the whole show, which is a single point of failure. But even more worrying, researchers figured out that those model updates, the learnings that get sent back, they aren't perfectly anonymous. A clever attacker could potentially reverse engineer them to figure out sensitive details about the original patients. It's like a tiny crack in the armor, but when you're talking about medical privacy, even a tiny crack is way too big.
So to seal that crack for good and build a system that was truly secure, researchers needed something totally new, something decentralized from the ground up and built with privacy as its absolute #1 priority. And that brings us to DeFi. The name itself basically tells you the entire story. It's decentralized, which means it gets rid of that central server. It's collaborative, so hospitals can still work together. And most importantly, it's privacy-preserving for multi-hospital data. This is a whole new level of security.
I mean, the upgrade here is huge. Standard federated learning needs that central hub. DCAP, no center at all. And where the old method had those potential privacy leaks, DCAP uses something called differential privacy, which is basically the gold standard for data security. It just makes the whole system tougher and way more scalable.
So what exactly is differential privacy? Okay, think of it like a mathematical cloaking device. It works by adding a very precise amount of statistical noise or randomness while the model is training. The end result is a rock-solid guarantee. You can study the final AI model all you want, and you will never be able to tell if my specific data or your specific data or anyone else's was part of that training set. The privacy of every single person is mathematically protected.
All right, so this all sounds fantastic in theory, but the real question, does it actually work in the real world? Well, researchers put DCAP through an absolute gauntlet, testing it on some of the toughest medical data out there to see if it could really deliver.
And they did not mince around. They tested it on 3 completely different, incredibly complex data sets. First up, trying to predict patient mortality using over 40,000 health records. Then, classifying individual cell types from thousands of human genomes. And finally, spotting diseases in a data set of over 250,000 chest X-rays. This was a serious stress test. And the results?
They were really, really impressive. For that patient mortality prediction task, the DCAF models were consistently more accurate than models trained at just a single hospital. They even beat the previous best privacy-preserving method out there. So this proved DCAF wasn't just safer, it was actually better.
How much better are we talking? Well, in some of these head-to-head tests, the models trained with DCAF performed up to 18.2% better than the next best private framework. That is a massive improvement.
And this, right here, this might be the most important part. For a long time, there's been this idea that if you want strong privacy, you have to sacrifice performance. But with DCAF, that trade-off is tiny. The models were almost as good as models trained with zero privacy protections, showing a performance drop of less than 3.2%. You get world-class privacy for a tiny, tiny price and accuracy.
Okay, but what about those sophisticated attacks? Researchers ran a simulation called a membership inference attack. That's where a hacker tries to guess if a specific person's data was in the training set. As you can see, the attack was way less successful against the DCAF model. It's just a much, much harder system to crack.
The final numbers showed that DCAF models were up to 16% less vulnerable to these kinds of privacy attacks. So this isn't just a promise of security, it's a tested, proven, more secure system.
So, what does this all mean for the future? Well, we are really looking at a brand new way of thinking about how we do large-scale, collaborative science with our most sensitive data.
I think the researchers behind the project put it perfectly themselves. They said that DCAF lets scientists conduct bigger studies and train better models by using data from all over the place, all without ever having to compromise patient privacy.
And that's really the big takeaway here. We don't have to choose between creating powerful AI and having strong privacy anymore. It's not a trade-off we have to make. Frameworks like DCAF are proving that it is absolutely possible to harness our collective intelligence to solve massive problems, all while respecting and protecting every single person's data.
And that leaves us with one final really big thought. We've been talking about medicine this whole time, but what happens when you apply this same idea to other fields with massive data silos? Think about global finance, or climate science, or even national security. What other huge global challenges could we finally start to solve if we could all learn from our data together without ever having to share it?